Okay, so energy, momentum are both conserved quantities, which means they are neither lost nor gained. Okay, in any collision, in any change, we don't lose or gain energy, or we don't lose or gain momentum. It's just transferred to a different object or transferred to a different type. We'll see that here in our different energy chapters, especially. Okay? Energy and work are both considered scalar quantities. What does that mean? They don't have what? Scalar quantities don't have one thing. Direction. Good, they don't have a direction. So scalars have only magnitude, which is the number, right? Okay. And this equation on the bottom, we'll get to it in a second, so don't worry about it just quite yet. Okay, energy and work are both scalar quantities. Okay, no direction, which is different from acceleration, force, velocity, displacement. All of those things are what types of quantities? Not scalar, but what's it mean to have both magnitude and direction? What's that called? Starts with a V. Vector. Vectors have both magnitude and direction. Okay, so force and acceleration is a vector. Okay, so what is work? Okay, I'm going to kind of give you the derivation of our equation down at the bottom, but work is essentially a change in energy. Okay, so you can write that down first, and then I'll kind of walk you through the equation that goes with it. Okay, so work is essentially kind of a change in energy. Okay, when something is transformed, we consider work being done on it. Okay, so work is the product of the magnitude and displacement times the component of the force that's parallel to our displacement. Okay, so it's force times displacement, but the force that we're talking about has to be parallel or in the same plane as our displacement. Okay, and I'll kind of show you that here in a little bit, but just kind of mull that over for a second. Okay, if we're applying a force that does work on an object, the force has to be parallel, or we have to use at least the parallel component of that force. Okay, so here's our equation for work, our simplest equation for work. Work, which is just a capital W, is equal to force times displacement. Units. If you wanted to guess the units for work, what would you think they would be if we're looking at force times displacement? What's the unit for force? Newton. And what's the unit for displacement? Meters. Okay, that's how you find units. Newton times meters, because it's force, which is newtons, times meters, which is times displacement, which is in meters. Okay, so that's the essential unit of our work quantity, but we kind of changed the name here in a little bit, and I'll show you that. Okay, but I want you to be able to figure that out by yourself. You should be able to see that your units are Newton meters. Okay. Force parallel is what we consider the force component that's parallel to our displacement. Okay, so we just talked about in order to calculate work, we have to take force times displacement, but force has to be the parallel component. So in this equation, if we're applying a displacement that's horizontal, yet our force is being applied at an angle, we have to find the parallel component, which in this case would be cosine. Okay, so anytime our displacement is horizontal, we can use this formula to find work that's being done. Okay, so in this case, our displacement's going to the east, so we use cosine of theta. Okay, anytime that our displacement is horizontal, but our force is being applied at an angle, we're going to use that cosine. Okay, if our displacement was vertical, then we might use sine instead. Okay. Example here. Okay. If we push a grocery cart 50 meters by exerting a horizontal force on the cart, how much work would be done on the cart? So if I have my grocery cart here, if I have my grocery cart, that's all I got for a grocery cart. Okay. If I'm applying a horizontal force, that means I'm pushing it Probably. And I'm probably not pulling it, but either way I'm going horizontal, so it doesn't really matter if I'm pushing or pulling it. But my force is 30 newtons. Okay? Is my displacement here going to be vertical or horizontal? Am I lifting the cart? Or am I pushing the cart? So my displacement is going to be 50 meters, which is horizontal. Okay? Are these two lines parallel to each other? Yes, so it works. Okay, we don't have to do cosine theta because this force is already parallel to our displacement. So we don't have to use cosine theta. Okay? So if I'm going to find work, I'm going to take force times displacement, which is equal to 30 times 50, which gives me 1,500 Newton meters. Yeah? Okay, did you all get that? Good. Okay, this one's simple, simple, simple. Okay, but we need to understand how we find that force component, and we have to pay attention to whether or not our displacement is horizontal or vertical or at an angle or wherever our displacement is. Okay? So the unit for work is in joules, which is a capital J. Okay? And 1 joule is equal to 1 Newton meter, so it's an exact conversion. Okay? So we give that work and energy both have the unit joules. I want you to think about both of these questions and see if we can come up with an answer for these. So think about them for just a couple minutes, talk with the person next to you or the people surrounding you, see if you can come up with an answer for these. Okay? Okay, so basically we can apply a force yet have no work done if there's no displacement, and when we carry an object, we have no work done either unless it's moving vertically as well, which in this case it was not. Okay, so the difference in these two things is that if I'm pushing a textbook on a table, let's say I'm applying a force, pushing a textbook, it's moving, I'm doing work, we have to ask the question, are we solving for the work done by me, or are we solving for the work done on the object? Those values will be the same, but we have to determine which one we're looking at. Okay, are we looking at the work done by me, or the work done on the textbook? The numbers will be the same, but we do have to make a specification there about what we're looking at. Okay, and this last one says we must specify whether the work is done due to a particular force, like the parallel component of our force, or whether it's the net force or the net work done. Okay, so this one takes just a little bit of explaining, and we will look at some specific examples of this here in just a second. Okay. There can be work done by an applied force, like me pushing the object. There can be work done by the frictional force. There can be work done by a gravitational force. There can be work done by lots of different things. Okay? So we have to pay attention to whether we're solving for the net work, which means we would look at the net force, or if we're solving for the work due to gravity or the work due to friction or any of those types of things. Okay, there's lots of different ways we can solve for work. And sometimes it'll ask you for the net, which is the overall, and sometimes it will ask you for the work due to gravity or the work due to frictional force or something like that. Okay, so we have to pay attention to what we're actually solving for. Go ahead and get this written down, or write down as much as you need. You don't have to write it down word for word, but we're going to start solving this problem here in just a second. So I want you to kind of get it written down first, and then we'll go through it together. All right. So I want you to kind of take a look at this diagram that's drawn here. And what's it called when we draw a diagram of forces? What's that called? It's 3 words. Blank, blank diagram. What's it called? Yeah, free body diagram. Good. Okay, so this free body diagram, if we label these forces, okay, it tells us that it's pulled 40 meters, so this is our displacement here, 40 meters. 100 Newton force is exerted by an angle of 37 degrees. So if I'm labeling this, my 100 Newtons goes here, and my 37 degrees goes in this triangle right there. Right? Do we agree? Okay, and what would this force be labeled? if it says the floor exerts a frictional force, right? Wouldn't that be our frictional force then, opposing the motion? Okay. So force due to friction goes there. First thing that we need to do is solve for the parallel component of our force, which would be this side of our triangle, right? That goes parallel to our displacement. So if I want to solve for F parallel, I take 100 times sine or cosine? Cosine, since I already had it written up there. Okay, cosine of 37, which gives me F parallel equal to what? Make sure your calculator's in degrees, not radians. Okay, I got about 79.9. Do we agree there for our parallel force? Okay, we want to find the work done on the crate. It doesn't tell us work done by the applied force, doesn't tell us work done by friction. We want the whole overall net work. Okay, so we could do this a couple different ways. And I think the simplest way for us to do it is to solve for the net force and then take that times our overall displacement. Okay, so if I want to find the net force here, I take rightward forces minus leftward, right? Is this kind of coming back now? Okay, rightward forces minus left. So my rightward force is 79.9. My leftward force is 50 newtons, because that's what it tells us friction does to this force. It slows it down by 50 newtons. So that means our net force is 29.9 newtons. Okay, and that's equal to F net. Okay, so now if I have my force, I can take it times my displacement and get the work done on the crate. Perfect. Okay, I don't really have room to write it here, but our total work is equal to 1,194.4 joules. Okay, gotta have units on there, which is joules, capital J. Okay, do we agree by taking 29.9 times 40? And it could be a little different depending on where you round. Okay, there's another way that you could go about solving for this. If we wanted to find work done by the applied force, we would have taken 79.9 times 40. We could have found work done by friction, which is 50 times 40, and then we could subtract those two values. You could do it two different ways. Find the work done by each force, then subtract those, or you could find the net force and take that times the displacement. Okay, a couple different ways you can go about it. All right, we're going to try another one here that has to do with vertical instead of horizontal. Okay, a work done by hiker on a 15-kilogram backpack to carry it up a hill that has a height of 10 meters. We're going to solve this one kind of the opposite of the way we did the last one. So I showed you how to solve for the net force, then find work. Now we're going to solve for work done by each force and then find the net. So that way you see both different ways to do it. Okay? So let's find the work done by the hiker. Just the work done by the hiker. Not the net work on the backpack. Just the work done by the hiker to carry that backpack up the hill. Okay? So if we want to find the work done by the hiker, what's the displacement of the backpack from where it started to where it ended? What's the displacement? 10 meters, right? We only care about the height because what's the force that he's applying? Is it vertical or horizontal? Vertical. That means we only care about the vertical height that the backpack travels. We don't care how it got up the hill. We just care about the fact that it ended up 10 meters above where it started. Okay? So the work done by the hiker goes with this force done by the hiker. So force of the hiker, I'm just going to put a little h there, is equal to what? What is he overcoming in order to carry that backpack? Gravity. Okay? So the force on the hiker is going to be the weight of the backpack times gravity because he's doing that work to overcome gravity. Okay, so the force that the hiker is having to exert is equal to basically the gravity that's pulling it down, because the backpack's not moving up and down on the hiker's back. It's staying steady. Okay, so he's doing just enough work or applying just enough force to overcome gravity. Okay, which is 147 newtons. So the hiker is applying 147 newtons worth of force to just keep that backpack up on his back, to not let it pull him over, to not let it carry it high or anything. He's doing just enough to keep it still. Okay? So when we solve for work, we're going to take force times displacement. So force of the hiker is 147. We said we just solved for. And what did we say his displacement was? 10 meters. Okay? And we only care about the vertical displacement because this is a vertical force. Okay, and no, that's a little bit tricky because we think that how far he actually walked is a part of it, but it's not. Okay, because this is not parallel to the force. Our displacement is our vertical displacement. Okay. Questions here? So this is work done by the hiker. So I'll put work sub H. Okay, work done by the hiker only. Okay, we just found that. Now we're going to find work done by gravity. What's gravity doing basically to pull that backpack back down? Okay, so if we want to find the force due to gravity here, we take mass times gravity, which means F sub g is equal to 15 times 9.8 also. And does gravity act while he's climbing up the 10 meters? Yes, it does. So work done by gravity is 147 joules times 10 meters. Okay, and work due to gravity then is 1470 joules. Okay, so why does it make sense that those two are equal to each other? Does it make sense that they're equal to each other? Yeah, why does it?
Because the backpack's connected to the guy.
Yeah, and he's moving at what? Constant velocity. And what do we know about the net force of something moving at constant velocity? 0. Okay, so overall net work on our backpack means to find the net work, we take up minus down, right? Our force of the hiker, or our work done by the hiker, was going up. The work done by gravity was going in the downward direction. So I take 1470 minus 1470, and I get 0 joules. Okay, so I know this seems counterintuitive that no work is being done. It might feel like this hiker is doing a lot of work, right, carrying that backpack. But technically speaking, no work was being done. Okay, because the backpack wasn't accelerating in the upward direction. It was just moving with the guy at constant velocity. Okay, which means the force that he is applying is equal to the gravitational force, which means technically no work was done. Okay? And I know that seems a little bit tricky to grasp, but we have to think about things that move at constant velocity. We don't have any work being done.